Okay, let's complete the story of the California story of California story on how it's trying to pay for reducing carbon emissions in the first place, including direct air capture done outside of California for the fuel you're buying or utilized in the product you may be using. So here is carbon intensity of fuels in terms of grams of CO2 equivalent per megajoule of energy produced. When you're in negative range, it would be about avoided methane emissions. So that's a credit. And here, so a farmer can do this by using a digester, composter, and other things. So it's not necessarily sequestering carbon, but it is avoiding emissions, so you can still get credits for that. And here are the various fuels with the bubble size showing the amount of fuel sold for transportations in California in 2017. 2018 is down here, and the conventional gasoline sits here, ethanol and fossil CNG are here, and so on. So the biodiesel, renewable biodiesel, so you can see various amounts are sold based on the or various flavors of biodiesel and renewable diesel, for example, being sold with different carbon intensities. So not all biodiesels are the same, not all hydrogen you buy is the same, etc. It's like the octane rating of the gasoline you would buy, for example. Okay, biocompressed natural gas, bioliquid natural gas, electricity production here, and so on. And people are earning credits. So this is the diesel dollar per diesel gallon equivalent displaced by cellulosic fuel. This is advanced biofuels. RIN is renewable identification number, which is used to track various uses. This is the low carbon fuel standard credit one earns. So this is going from August 2016 to August of 2020, so very recent, and you can see the various uses of cellulosic and advanced biofuels and the resulting credits earned by whoever the parties are that are replacing their diesel with these. So then they can sell these credits for whatever, for earning money or for future credits. Okay, so whenever we do direct air capture, obviously we have to be sure that the life cycle analysis shows that the energy used to do the air capture actually doesn't result in more than compensating for the amount of CO2 captured. Okay, so this is just looking at various ways of capturing CO2 from the air and its use or storage, and the amount of heat and electricity used in million tons of oil equivalent or million tons, megatons of CO2. Okay, it's a unit exchangeable there. So liquid direct air capture, when it's stored or used, needs certain amount of heat and electricity. So any CO2 you capture has to be obviously much more than that. Again, this comes down to, as we said, the cost per ton of CO2 as well, right? So liquid direct air capture, when used, uses similar amount of heat, but it requires much less electricity when it's directly used instead of stored as liquid. Solid direct air capture, when stored like dry ice, requires more heat, obviously, to cool it and store it as solid, and more electricity as refrigeration, let's say. And when it's used, it uses similar amount of heat but less electricity. I'm just showing that to say that none of this is a free meal. Everything has to be done as a life cycle. So what do we mean by use of carbon dioxide? I already briefly mentioned it, but let's look at it more carefully, and I will show another figure of this just to re-emphasize the point. So they have direct and other indirect uses. In the direct use, you just use it for making food and carbonated drinks, for example. That's not necessarily sequestration, it's just the use, because whatever you put into a carbonated drink is going to be released when it's consumed. Enhanced oil recovery, so it's pumped into the oil wells to force out more of the remaining oil from the little nooks and corners. So that's also not going to be reaching supercritical point and staying hidden, so that's also temporary. So these are uses, not sequestrations. Chemical and biological transformation for manufacturing chemicals and materials, polymers and plastics. So instead of using petroleum, we can use CO2, organic chemistry and minerals, or for manufacturing synthetic fuels and designer fuels. Okay, so here are some other examples. Independent study of CO2 science. Construction materials, we talked about cement, concrete, asphalt, aggregate, timber, super hardwood. Industrial gas and fluids, fuels, polymers, chemicals, new materials, and agriculture and food. We will talk about this a little bit more. Algae-based food or animal feed, microbial fertilizer, biochar, biopesticides, and biocosmetics. Okay. Graphene, which is a material that's getting a lot of attention and may have lots of new applications, which also go into, let's say, green technology, in which case increased use of CO2 into graphene could be a win-win situation as well. Okay, so all of these are kind of conceptual, I would say at this point. None of them have a solid scalable application that has shown to be having huge market value as of yet. Okay, so the question is, where are they headed in the coming years, and what are the potentials in terms of use of CO2 from direct air capture? Okay, there is the technology for direct air capture, its efficiency, its use of electricity and heat, and then the use of the CO2 that is then captured. So in a circular economy sense, maybe that will add up to something very valuable in terms of bending the curve and getting us towards staying below 2 degrees centigrade, and then dream of going down to 1.5 degrees. Yes.